Hold a ruler against the edge of a table and you can read its length straight off the marks. Reach for a finer tool and you can measure the width of a hair, then a single cell, then things far smaller than light itself. But there is a length so small that no tool could ever measure beneath it, and not because our instruments are too crude, but because the universe itself closes the door, turning any attempt to look that closely into a tiny black hole that swallows the very thing you wanted to see. That length is called the Planck length, and it is about a millionth of a billionth of a billionth of a billionth of a meter. We're going to build up to it slowly, one plain step at a time, starting from the simple act of measuring. If you like taking one idea apart gently and completely, consider subscribing. So what could possibly stop a perfect instrument? Pick up a wooden ruler and lay it along the spine of a book. The marks tell you the length and you trust them without a second thought. Measuring feels like the plainest act there is. You set one thing beside another thing whose size you already know, and you read off where the two line up. A ruler works because someone agreed long ago how far apart the marks should sit, and every ruler since has copied that agreement. So when you say a book is 20 centimeters tall, you are really saying it matches a standard, kept safe and copied carefully, that the whole world has chosen to share. But look closer at the ruler itself. The marks are thin black lines, and a thin line still has width. If you tried to measure something smaller than the gap between two marks, the ruler would simply shrug. It cannot tell you about anything finer than its own smallest division. Every measuring tool carries this built-in flaw. A bathroom scale that reads in whole kilograms cannot weigh a feather. A clock with only an hour hand cannot time a sprint. The tool can only speak in the size of its own steps. So the natural move, whenever you want to measure something smaller, is to find a finer tool. You reach for a tool with smaller steps, with marks closer together, with a sharper edge. And for most of human history, that is exactly how progress in measurement went. Each generation built a slightly finer instrument than the one before, and each finer instrument opened a slightly smaller world. The width of a coin gave way to the width of a thread, the thread to the fibres inside it, the fibres to things no eye could catch at all. This raises a quiet question that sits underneath everything we're going to explore. If finer tools keep opening smaller worlds, does the smallness ever end? Is there a bottom? You could imagine the answer being no, that with enough cleverness and enough patience, we could always build a sharper ruler and measure something smaller still, forever, with no flaw anywhere. That feels like the natural guess. Nothing in the simple act of measuring seems to forbid it. Hold on to that guess, because the whole story bends around it. The surprise waiting at the end is that there is a flaw, a smallest length below which no measurement can ever reach. And the reason is not that we're too clumsy or too poor or too early in history to build the right tool. The reason is built into the universe. The closer you try to look, the more the universe pushes back, until the very act of looking destroys the thing you wanted to see. For now, set that aside and stay with the simple picture. Measuring is matching. A tool can only measure down to the size of its own smallest step. To go smaller, you build a finer tool. That sentence is the seed of everything that follows, and it is worth carrying with you, because we are going to follow it all the way down until it breaks. The length where it finally breaks has a name. It is called the Planck length, and it is so small that the word small starts to lose its grip. Written out in meters, it begins with a decimal point followed by 34 zeros before the first real digit appears. We will learn that number slowly, step by step, and by the time it arrives it will feel almost inevitable. But the road there starts here, with a ruler against a book and one honest question. How small can a tool measure, and what could possibly stop it? Let us start by watching the tools get sharper. For most of history, getting a finer measurement meant carving finer marks. The earliest rulers were knotted cords and notched sticks, and the people who used them measured in body parts, the width of a thumb, the length of a forearm, the stride of a foot. These were rough, and they changed from person to person, but they worked for fields and timber and cloth. A merchant did not need to know the width of a hair. He needed to know how many bolts of fabric filled a cart. Then trade grew, and rough was no longer good enough. Builders and toolmakers wanted edges that matched, parts that fit, lengths that meant the same thing in two different cities. So craftsmen learned to divide a length into ever smaller equal pieces, scoring lines closer and closer together on metal and glass. By the time of careful clockmakers and instrument builders, a skilled hand could rule lines so fine they crowded against the limit of the naked eye. And there sat the next wall, the eye itself. A healthy human eye can separate 2 points only if they sit far enough apart on the back of the eye to land on different light-catching cells. Push 2 marks closer than that, and they blur into one. You can rule 100 lines in a millimetre, but if your eye cannot split them, the fineness is wasted. So the problem shifted. It was no longer only about carving sharper marks, it was about seeing them. That is where the lens entered the story. A curved piece of glass bends light, and a well-shaped lens can take the tiny image of a small thing and spread it across the eye, making it appear larger than it is. Reading stones, simple magnifying lenses, were used for centuries to enlarge text. Then, around the end of the 1500s and into the 1600s, lens makers in the Low Countries learned to stack lenses, and the microscope was born. One man took it further than anyone expected. Antony van Leeuwenhoek was a cloth merchant in the Dutch city of Delft, not a trained scientist, and he ground tiny glass beads into lenses of astonishing power. His little brass instruments were barely larger than a thumb, and through them he became the first person to see bacteria, the swimming things in a drop of pond water, the structure of muscle, the cells of blood. He guarded his lens-making methods closely and never fully shared them, but the worlds he reported were real, and they were teeming. With each better lens, the smallest visible thing got smaller. A grain of sand, then a single thread of silk, then a blood cell, then a bacterium. The trend was clear and encouraging. Build a sharper instrument, and a smaller world opens. The pattern from the last chapter held perfectly. Measuring is matching, and finer tools match finer things, and there seemed to be no end in sight. But Van Leeuwenhoek and the lens makers who followed him were quietly bumping into a wall they could not see and did not yet understand. No matter how perfectly they ground their glass, no matter how cleverly they stack their lenses, the very best microscopes all stalled at roughly the same smallness. Push past it, and the image did not just get faint, it got blurry in a way no polishing could fix. 2 tiny things close together refused to separate, smearing into a single smudge. For a long while, this looked like a problem of craftsmanship, something a better grinder would someday solve. It was not. The blur came from the nature of the thing doing the seeing. To understand the wall, we have to stop thinking about the glass and start thinking about the light passing through it. Because light, it turns out, is not a perfectly fine needle. Light has a size of its own. We see by light. That sounds almost too obvious to say, but it is the hinge of this whole chapter, so it is worth slowing down on. When you look at anything, light bounces off it, travels to your eye, and forms an image. A microscope does the same thing in a fancier way. It gathers the light coming from a small object and bends it into a larger picture. So whatever the smallest thing a microscope can show, it is the light that carries the news, and the messenger has limits. For a long time, people argued about what light actually is. Isaac Newton thought of it as a stream of tiny particles, little corpuscles flying in straight lines. That picture explained sharp shadows and the way light reflects off a mirror. But a Dutch contemporary, Christian Huygens, argued that light is a wave, a spreading disturbance like ripples on a pond. For a century, Newton's fame kept the particle picture on top. Then, in the early 1800s, an English physician named Thomas Young settled it with a beautifully simple experiment. Young was a remarkable mind who also helped decode Egyptian hieroglyphs, and he had a knack for seeing to the heart of a problem. he let light pass through two narrow slits side by side and fall on a screen behind. If light were simply particles flying straight, he would have seen two bright stripes, one behind each slit. Instead, he saw many stripes, bright and dark in an even pattern, marching across the screen. That pattern is the signature of waves. When two sets of ripples overlap, they add where crest meets crest, making a taller wave, and they cancel where crest meets trough, flattening to nothing. The bright stripes were the places where the light from the two slits arrived in step and reinforced. The dark stripes were where it arrived out of step and cancelled. Particles flying straight could not do that. Only waves could. Light, Young showed, spreads and overlaps and interferes, exactly as ripples do. So light is a wave, and a wave has a length. The wavelength is the distance from one crest to the next, and for visible light it is tiny but not zero. Red light has a wavelength of about 700 nanometers, and violet light about 400 nanometers, where a nanometer is a billionth of a meter. To picture that, take a human hair, which is roughly 80,000 nanometers across. A wave of green light is something like 100 times finer than that hair. Small, but real, and that small size is about to matter enormously. Here is the everyday picture to hold. Think of ocean waves rolling toward the shore and meeting a row of pilings. If the pilings are far apart compared to the spacing of the waves break against them and you can clearly tell where each piling sits, just from how the water piles up. But if the pilings are much thinner than the gap between the water barely notices them. The waves roll past almost undisturbed, and the fine detail of the pilings leaves no mark on the water. Light works the same way. To carry sharp news about an object, the light's wave has to be smaller than the detail you want to see. When the object is much smaller than the wavelength of the light simply flows around it and brings back only a vague, smeared report. The detail is there in the world, but the messenger is too coarse to carry it. That is the real reason Van Leeuwenhoek's finest lenses stalled. The glass was not the problem. The light was, and the man who turned this insight into a hard, exact wall was a German physicist working in a lens factory who wrote down a number that the best microscopes still obey today. His name was Ernst Abbe, and in the 1860s he was a young physics professor in the German university town of Jena, short of money and quietly brilliant. A microscope maker named Carl Zeiss had a workshop in the same town, and Zeiss was frustrated. He could build fine microscopes, but he built them by trial and error, grinding and testing, with no theory to tell him what he was doing right or wrong. He hired Abbe to find the theory. The partnership changed both their lives and changed the science of seeing. Abbe worked through the physics of how a lens forms an image from waves, and he arrived at a hard flaw. He found that a microscope using ordinary light cannot clearly separate 2 points that lie closer together than about half the wavelength of that light. Not because the glass is imperfect, but because of the wave nature of light itself. For green light, half the wavelength is roughly 250 nanometers, a quarter of a thousandth of a millimeter. Anything finer than that smears into a blur no matter how perfect the instrument. This flaw is called the diffraction limit, and diffraction is the key word. Diffraction is the tendency of waves to bend and spread when they pass an edge or squeeze through a gap. You have heard it without naming it. Stand around a corner from someone shouting, and you still hear them, because sound waves bend around the wall. Light bends too, just by a far smaller amount because its waves are so short. When light from a tiny point passes through the round opening of a lens, diffraction smears that point into a small fuzzy disk rather than a perfect dot. Picture 2 stars seen through a telescope, or 2 tiny lamps seen through a microscope. Each one, because of diffraction, shows up not as a clean point but as a little glowing smudge. If the 2 lamps are far apart, you see 2 separate smudges, no trouble. Bring them closer, and the smudges start to overlap. Bring them closer still, and the 2 smudges merge into one shapeless blob, and no amount of focusing can pull them apart again. The moment they merge is set by the wavelength of the light, and Abbe pinned it down with an equation. So the size of the messenger sets the floor. To honour van Leeuwenhoek's instinct, a sharper tool opens a smaller world, but only down to about half a wavelength of whatever light you're using. With visible light, that wall sits near 200 nanometers. You can polish your lenses for 1,000 years and never break it with ordinary light, because the limit lives in the light, not the glass. Abbe's number was so reliable that it became a design tool. Microscope makers stopped guessing and started calculating. The Zeiss workshop, now armed with theory, made instruments of a quality the world had not seen, and Abbe, the once poor professor, became a wealthy man and a generous one, pouring his fortune into a foundation that still bears the company's roots. His human detail is a kind one. He used his wealth to shorten working hours and guarantee pensions for the factory's workers, unusual for the time. But the diffraction limit, however firm, contained its own escape hatch, hidden in plain sight inside Abbe's own rule. The flaw depends on the wavelength of the light. Half of a large wavelength is a large flaw. Half of a small wavelength is a small flaw. So the obvious next move is not to polish the glass at all. It is to change the light. Use a shorter wave, and the flaw drops. That single idea, use a shorter wave, is the thread we follow next, and it leads straight out of visible light into something far sharper. If the flaw is half a wavelength, then shrink the wavelength, and the flaw sinks with it. That is the whole idea of this chapter, and physics took it seriously and ran. Visible light, the light our eyes evolved to catch, is only a thin slice of a much wider family. That family is the electromagnetic spectrum, and it stretches far past what we can see, in both directions, all made of the same kind of wave, differing only in length. On the long side of visible light sit infrared, microwaves and radio waves, with wavelengths from a fraction of a millimeter up to meters and beyond. Those are too coarse for our purpose. We want to go the other way, to the short side, where the waves get smaller and the flaw drops. Just past violet, the shortest light our eyes can see, lies ultraviolet, with wavelengths down around 100 nanometers and below. A microscope built to use ultraviolet light can resolve detail finer than any visible light microscope, simply because its messenger is smaller. Keep going shorter and you reach X-rays. An X-ray is the same kind of wave as visible light, the same kind of ripple in the electromagnetic field, but its wavelength can be smaller than a single atom, down around 1/10 of a nanometer. That is the scale of the spacing between atoms locked in a crystal, and this is where the shortwave idea paid off in one of the most important discoveries of the 20th century. In 1912, a German physicist named Max von Laue had a thought. If X-rays really are waves with a wavelength near the spacing of atoms in a crystal, then shining them through a crystal should make them diffract, just as light diffracts through a fine grating, producing a pattern of spots. The experiment worked. The X-rays came through the crystal and landed on a photographic plate in a neat, ordered array of spots, the unmistakable signature of waves meeting a regular structure. It proved two things at once. X-rays are waves, and crystals are built from atoms arranged in orderly repeating patterns. A father and son in England, William Henry Bragg and William Lawrence Bragg, then turned that pattern into a method. They worked out how to read the spots backward, using the angles and brightness to calculate exactly where the atom sat inside the crystal. The younger Bragg was only in his early 20s, still a student, when he found the key relationship. With it, X-rays became a ruler for the atomic world, measuring the distances between atoms directly. Decades later, the very same technique revealed the twisting shape of the molecule of life, by reading the X-ray pattern scattered from fibres of it. So the pattern from the early chapters held once more and held beautifully. Want to see something smaller? Use a shorter wave. Visible light stalls near 200 nanometers. Ultraviolet pushes lower. X-rays reach down to the size of atoms and the gaps between them. Each step to a shorter wavelength was a step to a smaller visible world, exactly as Abbe's rule promised, and exactly as Van Leeuwenhoek's instinct foretold. But notice something quietly building underneath. Each shorter wave is a more energetic wave. Ultraviolet light carries more energy than visible light, which is why it burns your skin where visible light only warms it. X-rays carry far more, enough to pass through flesh, and, in large doses, to damage living cells. The shorter the wave, the more punch it packs. We have not made anything of that yet, but the cost is starting to show. Sharper sight is coming at the price of more energetic probes, and that price will eventually become the whole story. Before we reach that reckoning, there is one more astonishing turn. It is not only light that comes in waves, matter does too, and a young French aristocrat saw it first. In 1924, a French graduate student named Louis de Broglie wrote a doctoral thesis with an idea so strange his examiners were not sure what to do with it. De Broglie came from an old noble family and had first studied history before turning to physics, drawn in by the puzzles his older brother, also a physicist, brought home. His thesis asked a simple, daring question. If light, long thought to be a wave, can also behave like a stream of particles, then might particles of matter, long thought to be tiny grains, also behave like waves? It sounded backward. An electron is a speck of matter, a little bit of stuff with mass. A wave is a spreading ripple, seemingly nothing like a grain. But de Broglie had noticed how nicely the two pictures had merged for light, and he proposed a clean rule. Every particle, he said, has a wavelength, and that wavelength gets shorter the faster the particle moves and the more massive it is. A slow light particle has a long wave, a fast heavy particle has a short one. For everyday objects, this wave is hopelessly tiny, far too small to ever notice. A thrown baseball has a wavelength so much smaller than the ball, smaller even than an atom, that it means nothing for how the ball flies. That is why we never see chairs and people ripple. But for something as light as an electron, the wave is not negligible at all. A moving electron can have a wavelength comparable to the size of an atom, or smaller, depending on how fast it goes. His examiners were uncertain enough that they sent the thesis to Albert Einstein for an opinion. Einstein read it and recognized at once that it was right and important. With that endorsement, de Broglie's idea stood, and within a few years it was confirmed in the most direct way possible. Experimenters fired a beam of electrons at a crystal, just as von Lauer had fired X-rays, and the electrons came through in the same kind of diffraction pattern, the same array of spots that only waves can make. Electrons, undeniably particles, were also undeniably waves. De Broglie received the Nobel Prize, a rare honour for work first laid out in a thesis. This was not just a curiosity. It was a new and powerful ruler. Remember the rule from the last chapters. To see something small, use a short wave. Electrons, when sped up, have wavelengths far shorter than visible light, far shorter even than the electron sits still. So a microscope built on electron waves should see much smaller things than any light microscope ever could. That machine was built. The electron microscope fires a beam of fast electrons at a sample and uses magnetic fields, shaped like lenses, to bend the electron waves into an image. Because the electron wavelength can be thousands of times shorter than visible light, an electron microscope can resolve individual viruses, the fine machinery inside a cell, and in its sharpest forms, the individual atoms in a piece of metal, showing up as an orderly grid of bright dots. The world that Van Leeuwenhoek opened a crack, the electron microscope threw wide, and the same quiet cost kept climbing. To make the electron's wave short, you have to make the electron fast, and to make it fast, you have to push it with energy. A short electron wave is a high-energy electron. The pattern that started as a gentle promise, sharper tools open smaller worlds, is hardening into a strict bargain. Smaller wavelength, higher energy. Always. If electrons sped up a little, let us see atoms. What could electrons sped up enormously let us see? That question leads out of the laboratory microscope and into a machine the size of a city, built to drive particles to nearly the speed of light and aimed at the smallest things we have ever probed. Run the rule to its limit. To see something small, use a short wave. To get a short wave from a particle, give it more energy. So to see the very smallest things, build a machine that pours staggering amounts of energy into single particles. That machine exists. We call it a particle accelerator, and the greatest of them is a ring buried beneath the border of France and Switzerland, run by the laboratory known as CERN. The ring is called the Large Hadron Collider. It helps to see an accelerator for what it really is. It is a microscope, a strange, enormous, indirect microscope, but a microscope all the same. A light microscope uses light waves to probe small things. An electron microscope uses electron waves. The Large Hadron Collider uses protons, the particles in the heart of every atom, accelerated until their waves are the shortest waves humanity has ever made. The shorter the wave, the smaller the detail it can probe, and these waves are small almost beyond imagining. The ring is about 27 kilometers around, a loop you could not walk in an afternoon, sunk 100 meters underground to keep it steady and shielded. Inside it, two streams of protons race in opposite directions, steered by thousands of powerful magnets and pushed faster on every lap by bursts of electric force. The protons are driven to within a whisker of the speed of light, so close that in the time it takes you to blink, a single proton has gone around the ring tens of thousands of times. At full speed, each proton carries the energy of a flying mosquito, which sounds gentle until you remember it is packed into something unthinkably smaller than a mosquito. Then the two streams are crossed, and protons smash head-on. In that collision, the enormous energy is concentrated into a space smaller than an atom's nucleus, and in that tiny, violent moment, the short waves of the protons probe distances far below the size of a single proton. The collision is the act of looking. The debris that sprays out, caught by detectors the size of buildings, is the image. From that debris, physicists read what sits at scales no lens could ever reach. This is how the Higgs boson was found in 2012, the particle tied to how other particles get their mass, predicted nearly 50 years earlier, and confirmed only when the collider reached enough energy to make it briefly appear. It is the same logic as reading von Lauer's spots, only turned up beyond all former limits. Higher energy, shorter wave, smaller probe, deeper look. So stand back and see the whole climb in one glance. The notched stick gave way to the lens. The lens stalled at the wavelength of light, so we use shorter light, then X-rays, then electron waves, then protons driven to nearly light speed. Every single step traded more energy for a smaller view. The accelerator is simply the far end of that road, the sharpest tool we have, and it works for exactly the same reason Van Leeuwenhoek's beads worked. A finer probe sees a finer world, and still the cost keeps rising, now to almost frightening levels. To look a little deeper than the Large Hadron Collider, you would need a noticeably more energetic machine. To look much deeper, you would need energies that dwarf anything we can build. The promise from the first chapter, that we could always go smaller with a sharper tool, is still technically holding, but the price tag is climbing toward the sky. It is time to stop treating that price as an engineering nuisance and start treating it as a law. Behind every step we have taken lies a single rule, and once we say it plainly, the flaw at the bottom of everything starts to come into view. Lay the steps side by side and the rule almost says itself. Visible light, with its wave a few hundred nanometers long, shows us things a few hundred nanometers across. X-rays, with waves the size of atoms, show us atoms. Electron waves, shorter still, show us the parts of atoms. Proton waves at the collider, shorter yet, show us inside the proton. In every case, to see something smaller, the probe had to carry more energy. There are no exceptions in the whole history. The rule is this: smaller things require higher energies to see. Why must this be? The deep reason is the wave. Any probe, whether light or electron or proton, has a wavelength, and it cannot bring back clear news about anything much smaller than that wavelength. To resolve smaller detail, you need a shorter wave. And both for light and for matter, a shorter wave means more energy. For light, shorter wavelength is bluer, more energetic light, which is why ultraviolet burns and X-rays penetrate. For matter, a shorter wave means a faster, more forceful particle. Either way, the road to small detail is paved with rising energy, and there is no other road. It is worth feeling how steep this is. The relationship is not gentle. To see something half as small, you do not pay a little more energy. Roughly speaking, you pay double. To see something 1,000 times smaller, you pay something like 1,000 times the energy. To probe the deep structure far below the proton, the energies needed climb into ranges that no machine on Earth, and perhaps no machine ever, could reach by ordinary means. The Large Hadron Collider, 27 kilometers of magnets, and the work of thousands of people, sits only a modest distance along this road. The far reaches are astronomically more demanding. Here is the everyday way to feel it. Imagine trying to feel the shape of a small object in the dark using only your sense of touch, but the only tool you are allowed is your fingertip. A fingertip can feel a coin, the ridges on its edge, the raised pattern on its face, but it cannot feel the individual grains of metal because the fingertip is far too broad. To feel something smaller, you would need a finer tip, a needle, then a needle finer than that. In the world of probing matter, making the tip finer means making the wave shorter, and making the wave shorter means spending more energy. The fineness of your touch is bought with energy, and the bill grows without mercy as the thing you want to feel gets smaller. So the comforting picture from the first chapter, that we can always build a sharper tool, survives, but it changes character. We can indeed go smaller. There is no wall in the rule itself that says we must stop at some particular size. But each step down costs more energy than the last, and the cost rises so steeply that going very far down would demand more energy than seems possible to gather. Already this hints that the road might not be endless in practice, yet a practical limit, set by how big a machine we can afford to build, is not the same as a true limit set by nature. So far we have only found a cost, not a wall. The wall, the real one, comes when this rule collides with two other deep facts about the universe. The first concerns what happens to energy when you try to pin a particle's position down very precisely. The second concerns what energy does to space itself. We have spent these chapters establishing the rule. Smaller means higher energy, always. Now we hand that rule to a young German physicist who discovered that nature sets a strict trade between knowing where a thing is and knowing how fast it is going. His trade is the next turn of the screw. In 1927, a German physicist named Werner Heisenberg, then only in his mid-20s, put forward an idea that unsettled even the people who admired it. Heisenberg was sharp, ambitious, and a little impatient, and he had been wrestling with the new quantum physics that was overturning the old comfortable picture of the world. What he found was not a flaw in our instruments, but a feature of reality, and it is called the uncertainty principle. Here is the everyday picture, and then the place it breaks. Think of a car driving past you. At any instant you feel you could say two things about it: where it is and how fast it is going. Position and speed seem like two separate facts, each knowable as precisely as you like, with no connection between them. Measure one more carefully, and it should not touch the other. For a car, that is true enough. Heisenberg found that at the scale of particles, those two facts are tied together, and tied in a way nothing can undo. The more precisely you fix a particle's position, the less precisely its momentum can be known, and the reverse holds too. Momentum, for our purposes, is just how much motion a thing carries, its mass times its speed. Position and momentum come as a pair, and the pair has a built-in budget. Spend your certainty on one, and the other must go fuzzy. You cannot have both sharp at once, no matter how clever or careful you are. This is not about clumsy measurement jostling the particle, though that image is sometimes used. It is deeper than that. The particle simply does not possess a perfectly definite position and a perfectly definite momentum at the same time. The sharpness is not hidden from us. It is not there to be had. Nature keeps the pair on a leash, and the length of that leash is set by a very small number called Planck's constant, a number we'll meet properly in a later chapter. For now, what matters is that the leash is real and its length is fixed. Experiments have confirmed this countless times, and it explains things that the old picture could not. It is why an electron does not spiral into the centre of its atom, which the old physics predicted it should. To sit exactly at the centre would mean a perfectly known position, which by the trade would demand a wildly uncertain, enormous momentum, and that costs too much. So the electron settles into a fuzzy cloud, a balance struck between being somewhere and not moving too violently. The very stability of atoms, the very existence of solid matter, rests on Heisenberg's trade. Now connect it to our climb. We have been trying to measure smaller and smaller lengths, which means pinning down position more and more precisely. To say where something is to within a tiny distance is to fix its position very sharply. And Heisenberg tells us that fixing position sharply forces momentum to become large and uncertain. A large momentum for a probe means a fast, forceful particle, which is to say a high-energy one. There it is again, from a completely different direction. To localize something within a small length, you're forced into high momentum, which means high energy. So two separate deep truths now point the same way. The wave rule said, smaller detail needs shorter waves, which need more energy. Heisenberg's trade says pinning a smaller position needs more momentum, which means more energy. They are two faces of one fact. The closer you look, the more energy you must bring, and now it is not a matter of engineering. It is a law woven into the fabric of the quantum world. The next step is to make this trade quantitative, to follow exactly how much energy a tiny position costs, because that rising energy is about to run headlong into gravity. Let us make Heisenberg's trade concrete and watch the energy climb. Suppose you want to know where a particle is to within some small distance. Call that distance your target. The uncertainty principle says that the smaller your target distance, the larger the uncertainty in the particle's momentum must be, and the two are linked tightly enough that halving the distance roughly doubles the minimum momentum. Push the target distance down by a factor of 1,000, and the momentum, and with it the energy, climbs by something like a factor of 1,000. To pin a position is, in the language of the last chapter, the same as probing a small length. So picture an experiment. You want to locate something within a billionth of a meter, the size of a few atoms. That requires a probe of a certain energy, modest by the standards of physics. Now you want 10 times finer, a tenth of a billionth of a meter, the size of a single atom. The probe must carry roughly 10 times the energy. Finer again, down to the size of an atomic nucleus, and the energy has climbed enormously. This is precisely the regime where you need an accelerator, a machine that pours real energy into a single particle just to fix its position that sharply. The everyday image is a stubborn one, so let us sharpen it. Imagine you're trying to find the exact spot where a tiny bell hangs in a pitch-dark room, and the only way to find it is to throw something at it and listen for the ring. A soft, slow beanbag will tell you roughly where the bell is, but it is too gentle and too broad to find the exact point. To locate the bell precisely, you need a small, fast, hard projectile, something that strikes a sharp point. The finer you want to know the bell's location, the harder and faster the thing you must throw. Knowing the position with great precision forces you to bring great energy to the throw. That is Heisenberg's trade, turned into a thing your arm can feel. So the cost of a point, the cost of saying exactly here and nowhere else, is energy, and the bill rises steeply as the point gets sharper. There is no upper limit in the principle itself. You can always demand a finer position, and the principle simply answers with a higher required momentum. On paper, you could imagine going down and down forever, paying more and more energy, with no wall in sight. The quantum trade alone does not stop you. It only keeps charging you more. But notice what is now sitting in our hands. To probe an extremely small length, we must concentrate an extremely large amount of energy into an extremely small region. That is the recipe forced on us by everything we have built so far. Smaller length, more energy, packed tighter and tighter into a smaller and smaller space. We have been treating that energy as just the price of admission, a number on a bill. We have not yet asked what that concentrated energy does to its surroundings, and that is the question everything has been building toward. Because energy is not a weightless abstraction. Energy, as one famous equation tells us, has mass. A great deal of energy concentrated in a tiny space is a great deal of mass concentrated in a tiny space. And mass does something to the universe around it that the quantum rules alone never accounted for. Mass pulls, mass bends. Mass, when packed tightly enough, can trap even light. So the energy we have been spending so freely to look closer is not free of consequences. We have been piling mass into an ever smaller spot without noticing. To see why that matters, we have to bring in the most famous equation in physics, and after it, the strangest force of all. The equation is short enough to fit on a ring. Energy equals mass times the speed of light squared. Albert Einstein wrote it down in 1905, in a brief addition to a longer paper, almost as an afterthought, during the astonishing year when he was a young clerk in a Swiss patent office, doing physics in his spare hours between reviewing applications. The idea inside it is one of the deepest in all of science. Energy and mass are not two different things. They are two forms of the same thing, and one can become the other. What the equation says, in plain words, is that mass is a tremendously concentrated form of energy, and that any energy you possess also carries a matching amount of mass. The speed of light squared is an enormous number, so a small amount of mass holds a vast amount of energy, which is why the sun can shine for billions of years on the slow conversion of a little of its mass, and why a small core of matter can release the energy of a city-leveling blast. But the equation runs both ways, and the other direction is the one we need. Energy carries mass. If you concentrate energy somewhere, you have concentrated mass there too. This is not a bookkeeping trick. It is measured directly, every day, at the very accelerators we discussed. When two protons collide at the Large Hadron Collider, their motion energy is converted into new particles with real mass that were not there before, conjured out of the energy of the crash. The Higgs boson, heavier than the protons that made it, was built from their energy of motion. Energy became mass in front of the detectors, exactly as the equation promised. The reverse, mass becoming energy, lights the sun and the stars. Now bring it back to our probe. We established that to look at a very small length, the uncertainty principle forces us to concentrate a very large energy into a very small region. By Einstein's equation, that concentrated energy is also a concentrated mass. The smaller the length we want to probe, the more energy we must pack in, and therefore the more mass we are packing into that tiny spot. Our probe, the thing we're using to look, gets heavier and heavier as we try to look closer and closer. The act of sharpening our view loads more and more mass into the very point we're trying to examine. Sit with how strange that is. When Van Leeuwenhoek looked through his little lens, the act of looking was gentle. The light he used weighed, for all practical purposes, nothing, and it left the pond water undisturbed. But as we drive the probe energy up to reach smaller and smaller scales, the probe stops being gentle. By the time we're trying to look at truly tiny lengths, the energy required is so vast that, turned into mass, it is a serious lump of mass crammed into a vanishingly small space. The looker is no longer a feather, it is becoming a weight, and mass, unlike a feather, is not a passive thing in the universe. Mass reaches out. Every bit of mass pulls on every other bit through gravity, the force that holds you to the ground and the planets to the sun. For most of our story, gravity could be ignored because the masses involved were absurdly small. A photon, An electron, even a fast proton, weighs far too little for its gravity to matter at all. But we are now concentrating mass into a tiny region without limit, and gravity, the weakest of forces in everyday life, has a way of becoming the most important force of all when mass is squeezed small enough. To understand what that squeezed mass does, we have to leave the quantum world for a moment and turn to Einstein's other great theory, the one about gravity and the shape of space. Einstein's first famous equation came in 1905. His deepest work came 10 years later, in 1915, and it was about gravity. He called it the general theory of relativity, and it replaced an old, comfortable idea of gravity with a stranger and truer one. For more than 2 centuries since Isaac Newton, people had pictured gravity as a force reaching invisibly across empty space, a pull between any two masses, acting at a distance through nothing. It worked beautifully for falling apples and orbiting planets. But Einstein saw that it was not quite right, and what he put in its place changed how we think about space itself. In Einstein's picture, gravity is not a force pulling across space. Gravity is the shape of space. Mass and energy bend the space and time around them, and other things, moving through that bent space, follow curved paths. They are not being pulled by an invisible string. They are coasting as straight as they can through a landscape that mass has warped. The Earth does not feel a tug from the Sun. The Earth rolls along the valley the Sun's mass has pressed into the shape of space, and that rolling is what we call its orbit. The everyday picture, imperfect but useful, is a heavy ball resting on a stretched rubber sheet. The ball makes a dip, and a marble rolled nearby curves toward it, following the slope, not because the ball reaches out and grabs it, but because the surface it rolls on is bent. Put a heavier ball on the sheet and the dip gets deeper, the curving sharper. Space, Einstein said, is something like that sheet, except it is 3-dimensional and woven together with time, and the dips are made by mass and by energy alike. The rubber sheet picture stops fitting in important ways, since real space has more dimensions and bends in directions the sheet cannot, but it carries the heart of the idea. Mass tells space how to curve, and curved space tells matter how to move. This was not just a prettier story. It made predictions the old picture could not, and they came true. It predicted that light itself, passing near a massive body, would follow the curved space and bend. And in 1919, during a total eclipse of the Sun, astronomers measured starlight bending around the Sun by exactly the amount Einstein had calculated. It predicted that time runs slower where gravity is stronger, and that has been measured too, precisely enough that the satellites guiding cars and phones must correct for it, or they would steer you to the wrong street. General relativity is not a guess. It is one of the most thoroughly tested ideas in all of physics. Now bring back our heavy probe. We have been concentrating more and more mass into a smaller and smaller region in order to look at tiny lengths. Einstein's gravity tells us what that does. It bends the space around that region, and the more mass we pack in, and the tighter we pack it, the deeper and sharper the bend becomes. A little mass makes a gentle dip. A great mass crammed into a tiny spot makes a steep, severe well in the shape of space. So now 2 of the universe's deepest rules are bearing down on the same point. The quantum rule forces us to concentrate ever more mass into an ever smaller region to look ever closer. The gravity rule says that concentrated mass bends space, more steeply as it grows. We are digging a deeper and deeper well in space at the very spot we're trying to examine. The question that decides everything is simple. How deep can that well get before something drastic happens? For the answer, we turn to a soldier doing physics by candlelight on a battlefield who found the edge past which the well becomes a trap. The man who first found the answer worked it out under the worst conditions imaginable. His name was Karl Schwarzschild, a respected German astronomer, and in 1915, when Einstein published his equations of gravity, Schwarzschild was serving in the German army on the Russian front of the First World War, in his early 40s, older than most soldiers, having volunteered. In the cold and noise of the front between his military duties, he read Einstein's brand new theory and did something Einstein himself had not yet managed. He solved the equations exactly for the simple case of the space around a single round mass. He sent his solution to Einstein, who was astonished, both that it had been done so quickly and that it had been done at all amid a war. Einstein presented it on his behalf. Tragically, Schwarzschild fell ill at the front with a rare and painful skin disease and died within months in 1916, never seeing how important his work would become. His name now sits on one of the most famous ideas in physics, a small justice for a life cut short. What Schwarzschild found, buried in his solution, was a special distance. For any given mass, there is a particular radius, a size, that depends only on how much mass there is. If you take that mass and squeeze it down inside that radius, the bending of space becomes so extreme that nothing, not even light, can climb back out. That distance is now called the Schwarzschild radius, and the surface at that distance is the edge of no return. The radius is astonishingly small for ordinary masses because gravity is so weak. To turn the entire Earth into one of these traps, you would have to crush it down until the whole planet fit inside a sphere about the size of a small marble, less than a centimetre across. To do the same to the Sun, you would squeeze it down to a ball a few kilometres wide. The mass stays the same. What changes is how tightly it is packed. Spread out, the mass makes only a gentle dip in space. Crushed inside its Schwarzschild radius, the same mass makes a well so steep that the sides become vertical, and there is no climbing out. Here is the everyday way to feel it. Throw a ball straight up and it comes back down, because Earth's gravity is too strong for the ball's modest speed. Throw it faster and it rises higher before returning. Throw it fast enough, about 11 kilometers a second from Earth's surface, and it never comes back at all. It escapes. That speed is the escape velocity, and it depends on how much mass you are fighting and how close to it you stand. The Schwarzschild radius is simply the distance at which the escape velocity reaches the speed of light. Closer than that, escaping would mean going faster than light, which nothing can do, so nothing escapes. Notice what this means for our probe. We have been concentrating mass into a smaller and smaller region. Every amount of mass has its own Schwarzschild radius, the size below which it becomes a trap. As long as our concentrated mass stays spread out wider than its Schwarzschild radius, all is well and we can keep looking. But if the act of looking forces that mass into a region smaller than its own Schwarzschild radius, the well snaps shut. Space closes over it. The thing that forms when mass crosses inside its Schwarzschild radius has a name everyone knows, even if its physics is strange. It is a black hole. And a black hole, as we are about to see, is exactly the wall that ends our long climb downward. A black hole is what you get when mass is packed inside its own Schwarzschild radius, and space closes over it so completely that nothing can get back out. The name was made popular by the American physicist John Wheeler, a gifted teacher with a knack for the right phrase, in the 1960s, though the idea had haunted physics since Schwarzschild's wartime solution. For decades, many physicists, including Einstein himself, hoped black holes were only a mathematical curiosity, something the equations allowed but nature would never actually build. Nature, it turned out, builds them readily. We now know black holes are real and common. When a very massive star runs out of fuel, its core collapses, crushing its mass inside its Schwarzschild radius, and a black hole is born. At the centres of galaxies, including our own, sit giant black holes millions or billions of times the mass of the Sun. We have watched stars whip around these unseen centres, felt the ripples in space when two black holes collide, and even made an image of the glowing gas circling the edge of one, a dark centre ringed by light, captured by a network of telescopes spanning the Earth. The thing Einstein doubted is now photographed. The defining feature of a black hole is its edge, the surface at the Schwarzschild radius, called the event horizon. It is not a solid shell. It is a boundary in space, a point of no return. Anything that crosses it, light included, can never come back, because coming back would mean outrunning light. From outside, you can never see in. Whatever falls past the horizon is lost to the outside universe forever, its news sealed away. The horizon is a one-way door. This is the wall our long climb has been heading toward, though we did not know it at first. Recall the bargain we have been forced into step by step. To look at a smaller length, we must concentrate more energy, which is more mass, into that small region. The smaller the length, the more mass, packed tighter, and we just learned that any mass packed tightly enough inside its Schwarzschild radius becomes a black hole, sealed behind an event horizon. So picture pushing the experiment to its extreme. You want to examine an incredibly small region of space. To do it, you fire in a probe of incredible energy, and by Einstein's equation, that energy is a large mass, concentrated right at the tiny spot you wish to study. If you demand a small enough target, the mass you're forced to concentrate there becomes so large, in so small a space, that it slips inside its own Schwarzschild radius. At that instant, an event horizon forms around the very region you were trying to see. A black hole appears precisely where you were looking, and once the horizon forms, the thing you wanted to examine is gone. It is behind the horizon now, sealed away, its information lost to you forever. Worse, you cannot even see inside the region. The black hole's horizon is a wall that no light, no signal, no probe can cross and return from. The act of looking too closely has not just failed. It has built a wall of darkness around the very thing you hope to measure, and there is no way around the wall, because the wall is made of bent space itself. This is the heart of why no tool can ever measure below a certain length. It is not crudeness. It is not poverty. It is that the energy required to look that closely makes a black hole, and a black hole hides what it surrounds. There is some smallest length below which any attempt to look simply seals itself off behind a horizon. To find exactly where that wall sits, we need to bring two specific sizes face to face, one from the quantum world and one from gravity, and watch the precise point where they cross. We now have two competing sizes, and the place they meet is everything. Both of them belong to the probe particle we're using to look, and both shrink or grow with its energy, but they move in opposite directions. Watching where they cross is how the bottom of measurement reveals itself. The first size comes from the quantum world. We have seen that a particle has a wavelength, and the more energy it carries, the shorter that wavelength becomes. There is a particular version of this for a particle of a given mass, called the Compton wavelength, named for the American physicist Arthur Compton, who in the early 1920s showed that light bounces off electrons like a ball off a ball, gaining and losing energy in measurable amounts. The Compton wavelength is, roughly, the smallest region within which you can sensibly pin a particle of that mass before the quantum fuzziness blurs it. Heavier, more energetic particle, smaller Compton wavelength. This is the resolution of your probe. The smaller it is, the finer you can see. So to look closely, you want this size small, which means you want your probe heavy. The second size comes from gravity. It is the Schwarzschild radius, the distance inside which that same mass becomes a black hole. Heavier mass, larger Schwarzschild radius. This is the danger zone of your probe. The bigger it is, the larger the region that gets swallowed behind a horizon. So to avoid making a black hole, you want this size small, which means you want your probe light. Look at the bind. The two sizes pull in opposite directions as you change the probe's mass. Make the probe heavier to sharpen your view, and the Compton wavelength shrinks, which is good, your resolution improves, but the Schwarzschild radius grows, which is bad, the danger zone expands. Make the probe lighter to stay safe, and the Schwarzschild radius shrinks, good, but the Compton wavelength grows, bad, your view goes blurry. You cannot win both at once. Improving one ruins the other. So as you turn up your probe's mass, two things happen together. The region you can resolve gets smaller, and the region that would collapse into a black hole gets larger. At low mass, the resolution region is much larger than the black hole region, so you are safe, and your view is the limiting factor. You can keep improving by adding mass, but you are walking the two sizes toward each other. The good size is shrinking, the dangerous size is growing, and they are heading for a meeting. The everyday way to feel this is a tug of war between two ropes tied to the same post, pulling opposite ways, where tightening your grip on one loosens the other. Pull the resolution rope, sharpen your view, and the black hole rope slackens dangerously toward you. Pull back from the black hole, stay safe, and the resolution rope goes slack and your view blurs. Somewhere in the middle is a single point where the two ropes are balanced, where neither can be improved without making the other worse. That balance point is special, and it is the bottom. At that crossing, the smallest region you can resolve has shrunk down to exactly the size of the region that would become a black hole. The finest thing you can see is the same size as the horizon you would create by trying to see it. Push past that point, make the probe any heavier to look any closer, and the black hole region overtakes the resolution region. The horizon swallows the very scale you are trying to examine. You can go no finer, because finer means hidden. That crossing point where the Compton wavelength and the Schwarzschild radius become equal is a specific length. It does not depend on which particle you chose or how clever your machine is. It falls out of the constants of nature themselves, and when you work out the number, a single, fixed length emerges, the same for everyone, everywhere. That is the Planck length, and in the next chapter we watch it drop out of the meeting of these two sizes. So set the two sizes equal and see what comes out. On one side, the Compton wavelength, the quantum resolution of the probe, which depends on the probe's mass and on the quantum of action, Planck's constant, and on the speed of light. On the other side, the Schwarzschild radius, the gravitational danger size, which depends on the probe's mass and on the strength of gravity and again on the speed of light. Set them equal, and a remarkable thing happens. The probe's mass cancels out. It vanishes from the answer entirely. That cancellation is the deep point. It means the crossing length does not depend on what you used to probe, or how heavy you made it, or how big your machine was. All the details of the experiment fall away. What remains is built only from three fundamental constants of the universe. The speed of light, which sets how fast anything can travel and ties space to time. The strength of gravity, which sets how strongly mass bends space. And Planck's constant, which sets the scale of the quantum world, the size of the leash in Heisenberg's trade. Combine those three numbers in the one way that produces a length, and out comes a single, fixed distance. That distance is the Planck length. Written in meters, it is about 1 6/10 times 10 to the power of -35. In plain words, you write a decimal point, then 34 zeros, and then the first real digits. It is, as the introduction promised, about a millionth of a billionth of a billionth of a billionth of a meter. The number is so small that ordinary comparisons strain to hold it. But let us try, because a number you cannot picture is not yet yours. Take a single proton, one of the particles in the nucleus of an atom, already so small that trillions would fit across the width of a hair. The Planck length is smaller than that proton by about the same factor that the proton is smaller than a city. Said another way, if you blew up a proton until it was the size of the entire observable universe, the Planck length, blown up by the same amount, would still be only about the size of a small tree. That is how far below everything familiar this length sits. It is not just small. It is small compared to the small compared to the small. And here is what the long climb has shown us about it. The Planck length is the size where our two limits collide, where the finest resolution you can buy equals the horizon you create by buying it. Try to measure any length shorter than this, and the energy you must concentrate to do it makes a black hole bigger than the thing you're measuring. The thing vanishes behind a horizon. So no measurement can return news from below the Planck length, not because of crude tools, but because the universe answers every attempt with a black hole. This is the wall the first chapter promised, and now we know exactly where it stands and why. Carry this plain sentence with you. The Planck length is the size at which the act of looking closer makes a black hole. That single line is the whole argument folded up. The wave rule and Heisenberg's trade said looking closer cost energy. Einstein's equation said that energy is mass. Schwarzschild and the black hole said that mass, packed small enough, seals itself behind a horizon. Put them together, and there is a smallest measurable length, and it is the Planck length. But notice what we have and have not shown. We have shown it is the smallest length we could ever measure. We have not shown it is the smallest length that exists, the smallest piece space is made of. Those are different claims, and the difference matters enormously. Before we wrestle with that honest distinction, we should meet the man whose name this length carries, and learn that he built it not as a wall, but as a dream of a universal language, long before anyone knew about black holes at all. The length carries the name of Max Planck, a German physicist who was, in temperament, almost the opposite of the daring young men who built quantum theory. Planck was cautious, formal, deeply conservative, a man who came to revolutionary ideas reluctantly and only because the evidence left him no choice. In 1900, he reluctantly proposed that energy comes in tiny discrete packets, the seed of all quantum physics, an idea he himself found uncomfortable for years. But a year before that, in 1899, he had already done something quieter and, in its own way, just as visionary. He had asked what a truly universal set of measuring units would look like. Think about how arbitrary our everyday units are. The meter was once defined as a fraction of the distance from the North Pole to the equator, then as the length of a particular metal bar kept in France. The second came from dividing up the day. The kilogram was a lump of metal in a volt. These units work, but they are human accidents, tied to the size of our planet and the length of our day, and the choices of old committees. If we ever spoke to a distant civilization, none of our units would mean anything to them. They have never seen our metal bar. Planck wanted units that any intelligent being anywhere in the universe would arrive at. Units built not from human history, but from the constants of nature itself. The numbers that are the same everywhere and for everyone. He realized that a few fundamental constants could be combined to produce a unit of length, a unit of time, a unit of mass, and so on, with no reference to Earth or humanity at all. He called them natural units. Today we call them Planck units, and the length among them is the Planck length we have been chasing. What is striking is that Planck built these units in 1899 purely out of a love of elegance and universality. He had no notion of black holes, no quantum theory yet, no inkling that the length he wrote down would later turn out to mark the edge of measurement itself. He was simply combining nature's constants in the only way that yields a length, the way we did in the last chapter, when the probe's mass cancelled out. He was looking for a common language, and he stumbled, decades early, onto a fundamental boundary of physics without knowing it was there. That is one of the quiet beauties of this whole story. The same length appears from two completely different directions. Planck reached it by asking for the most natural possible ruler, a unit any mind in the cosmos would recognize. We reached it by asking how closely anything can ever be measured before a black hole swallows the answer. Two different questions, one number. When that happens in physics, when a quantity shows up by separate roads, it is usually a sign that the quantity is telling you something deep about the world, not just about your method. Planck's life ran long and sorrowful. He lived through 2 world wars, lost one son in the first and another, executed by the Nazis in the second, and saw the German science he loved nearly destroyed. He stayed in Germany through it all, a figure of dignity in a collapsing world. His name now sits on the length at the bottom of measurement, on Germany's foremost research institutes, and on the constant at the heart of quantum theory. For a man who distrusted revolutions, he set off more than his share. To really understand the Planck length and the strange family of units around it, we need to meet the 3 constants Planck combined, the 3 numbers that the answer depends on. Each one has its own history, its own moment when a human being first pinned it down. They are the speed of light, the strength of gravity, and the quantum of action. and they are worth knowing one at a time. 3 numbers build the Planck length, and 3 numbers build the whole modern picture of the physical world. They are worth meeting properly, because each marks a frontier of physics, and each was wrestled into a measurement by real people over centuries. The first is the speed of light, written in physics as a lowercase c. For most of history, people assumed light was simply instantaneous, arriving everywhere at once. The first proof otherwise came in 1676, when a Danish astronomer named Ole Romer noticed that the moons of Jupiter seemed to fall behind schedule when Earth was farther from Jupiter and run ahead when closer. He realised the difference was the time light took to cross the extra distance, and from that he got the first real estimate of light speed. Later experiments on Earth, bouncing light off distant mirrors, refined it. We now know light travels at about 300,000 kilometres every second, fast enough to circle the Earth 7 times in the time it takes to say the word. That speed is the universe's ultimate limit, the speed nothing with mass can reach, and it ties space and time together into a single fabric. The second is the strength of gravity, written as a capital G, the gravitational constant. It tells you how strong the pull is between 2 masses of a given size at a given distance. Newton wrote the law of gravity in the 1680s, but never knew the value of this constant. It was finally measured in 1798 by an eccentric, intensely shy English scientist named Henry Cavendish, who hung 2 small lead balls from a delicate rod and watched them twist, ever so slightly, toward 2 larger lead balls placed nearby. The twist was tiny because gravity between tabletop objects is almost unimaginably weak, but Cavendish measured it, and in doing so he in effect weighed the entire Earth. Gravity's constant is a very small number, and that smallness, that weakness, will matter enormously in the next chapter. The third is the quantum of action, written as a small h, or in its most common form as h-bar, h with a line through it, which is Planck's constant divided by a certain factor. This is the number Planck found in 1900 when he was forced to assume energy comes in discrete packets to explain the colours of light glowing from a hot object. The constant sets the size of those packets, and more broadly it sets the scale of the entire quantum world. It is the length of the leash in Heisenberg's trade, the number that decides how tightly position and momentum are bound together. It is an extraordinarily small number, which is why the quantum world's strangeness stays hidden at the size of everyday things and only shows itself among atoms and particles. So there they are. The speed of light, the constant of the very fast and the very large, the gravitational constant, the number of mass and curved space, and Planck's constant, the number of the very small. Each rules a different domain of physics, and for a long time those domains barely spoke to one another. Light speed lives in relativity. Gravity's constant lives in Einstein's theory of curved space. Planck's constant lives in the quantum world of particles. The Planck length is the one place all 3 meet at once. It is built from all of them together, the only length you can make by combining the speed of light, the strength of gravity, and the quantum of action. That is why it sits at such a strange and deep frontier. It is the scale where relativity, gravity, and the quantum all become important together, the one length that asks all 3 theories to speak at the same time. And as we will see, when we force them to speak together at that scale, they begin to contradict each other. But first, those same 3 constants hide a genuine surprise in the unit of mass, one that catches almost everyone off guard. Here is where Planck units spring their biggest surprise. We have spent many chapters marvelling at how staggeringly small the Planck length is, far below anything we can reach. You would naturally expect every Planck unit to be that way, each one a tiny, unreachable speck at the bottom of the world. The Planck length is unimaginably small. The Planck time, as we will see, is unimaginably brief. So the Planck mass should be unimaginably tiny too, far smaller than any particle. That is the obvious guess. The obvious guess is spectacularly wrong. The Planck mass is about 20 millionths of a gram. in the world of human things that is minuscule, far too small to see or weigh on a kitchen scale, roughly the mass of a flea's egg or a barely visible speck of dust. But hold it next to the world it supposedly belongs to, the world of fundamental particles, and it becomes a giant. A single proton has a mass so small that you would need to gather something like 10 to the 19th protons, 10 billion of them, to add up to 1 Planck mass. Compared to the particles physics deals with, the Planck mass is not small at all. It is enormous, monstrously, absurdly large. Sit with how odd that is. The Planck length is far smaller than a proton. The Planck mass is far larger than a proton. The length is a speck below all specks, and the mass is a mountain above all the particles. They come from the same 3 constants, the same simple combination, and yet one lands at the very bottom of its world, and the other towers at the top of its world. That mismatch is not a mistake, it is a clue, and the clue points straight at gravity. The reason is gravity's astonishing weakness. We met it in the last chapter through that tiny gravitational constant Cavendish measured. Gravity is by far the weakest of the fundamental forces, weaker than the others by factors so large they're hard to write down. You feel this every day without noticing. A small magnet held in your fingers can pick a paperclip up off a table, which means that little magnet's pull beats the gravity of the entire Earth, tugging the clip the other way. The whole planet loses that contest to a toy magnet. That is how feeble gravity is, force for force. Because gravity is so weak, you need to pile up a tremendous amount of mass before its effects, like making a black hole, become important, and that is exactly why the Planck mass comes out so large. The Planck mass is, roughly, the amount of mass you would have to concentrate into a single particle's quantum fuzziness before that particle's own gravity became as strong as the other forces acting on it, strong enough to wrap space around it. Gravity is so weak that the mass needed to make it matter, at the scale of 1 particle, is colossal by particle standards. The weakness of gravity and the largeness of the Planck mass are the same fact, seen from 2 sides. This is the angle that many short videos on the Planck length skip entirely. They show you the tiny length and stop, leaving you thinking all Planck units are tiny. But the Planck mass tells a richer story. It is the reason the Planck length sits so far below everything we can reach. To probe down to the Planck length, you would need to concentrate roughly a Planck mass of energy into a single probe, and that is an energy so vast that no accelerator we could ever build comes remotely close. Gravity's weakness pushes the wall of measurement absurdly far down, out of all reach. The Planck mass anchors the other units too. Pair it with the length and the speed of light, and out come the last 2 members of the family, the Planck time and the Planck energy, each as extreme as the length in its own direction. The Planck length has partners, and the most natural of them is the Planck time. If the Planck length is the smallest distance that measurement can meaningfully speak about, the Planck time is, in the same spirit, the shortest interval that has any clear meaning, and the link between them is the simplest one in physics. The Planck time is just how long it takes light to cross 1 Planck length. Light is the fastest thing there is, so the time it takes to cross the smallest meaningful distance is the shortest meaningful tick of the universe's clock. That tick is almost beyond words. The Planck time is about 10 to the negative 44 seconds, a decimal point followed by 43 zeros before the first real digit. To feel how brief that is, consider this. In 1 ordinary second, the number of Planck times that pass is far, far greater than the number of seconds that have elapsed since the universe began, some 13.5 billion years ago. A single second, sliced into Planck times, holds more slices than the entire age of the cosmos holds seconds. The shortest tick makes our shortest human instance look like geological ages. The Planck time matters for one of the deepest questions we can ask, the beginning of the universe. When we run the expanding universe backward in our theories, toward the Big Bang, everything gets hotter, denser, and smaller. At a certain point going back, the whole observable universe is squeezed so small and so hot that gravity and the quantum world both become overwhelming at once, exactly the conditions where the Planck scale rules. That moment is the Planck time after the supposed beginning, the first sliver of an instant. Before it, at times shorter than the Planck time, our current theories simply stop giving sensible answers. We cannot describe the universe earlier than one Planck time after its start, not because we lack data, but because the laws themselves break down there. The Planck time is the edge of our story of the beginning. The other partner is the Planck energy, and it is extreme in the opposite direction. Where the Planck length and Planck time are absurdly small, the Planck energy, concentrated in a single particle, is absurdly large. It is the energy you would need to give one probe to push down to the Planck length, and it is something like the chemical energy stored in a full tank of gasoline, all packed into one subatomic particle. Imagine the entire energy that drives a car for hundreds of kilometers crammed into something smaller than an atom. That is the Planck energy, and it explains in one stroke why we can never reach the Planck length by force. Our greatest accelerator, the Large Hadron Collider, falls short of the Planck energy by a factor of about 1,000 trillion. To reach it head-on, you would need a machine of unimaginable scale. Together these units mark out a single regime, the Planck scale, where length, time, mass and energy all reach the values built from nature's three constants. It is the scale where the very small and the very heavy meet, where the quantum world and gravity can no longer be kept in separate rooms. Everything we have built points to this one frontier. The Planck length sets its size, the Planck time its tick, the Planck mass and energy the price of admission. We have now assembled the whole picture, the wall and the units that describe it. So let us state the central paradox as cleanly and plainly as we can, in a single tight argument, so that it sits in the mind whole. Why, exactly, must any attempt to look below the Planck length make a black hole? The next chapter says it in one breath. Let us gather the whole argument into one clear chain, because it deserves to be held complete, without any of the history or the side roads, just the bare logic from start to finish. This is the heart of why no tool will ever measure below the Planck length, said plainly enough to repeat to a friend. Start with what it means to measure a small length. To measure where something is, to within some small distance, you must probe it, and probing means hitting it with something, a wave or a particle. That is the first link. Measurement is probing, and probing means sending something in to look. Second link. To resolve a small distance, your probe must have a short wavelength, because a wave brings back no clear news about anything much smaller than itself. This was Abbe's diffraction limit and de Broglie's matter waves together. Short distance demands short wavelength. Third link. A short wavelength means high energy. For light, shorter waves are more energetic. For matter, shorter waves mean faster, more forceful particles. This held for ultraviolet, for X-rays, for electrons, for the protons at the collider, with no exceptions. The same truth comes from Heisenberg's trade, where pinning a position tightly forces a large uncertain momentum, which is high energy. Small distance demands high energy. Fourth link, high energy is high mass, concentrated in the small region you are probing. This is Einstein's equation. Energy equals mass times the speed of light squared, confirmed every day when collisions turn energy into new particles. The energy you pour in to look closely is, unavoidably, mass packed into the tiny spot you're examining. Fifth link. Mass concentrated in a small region bends space, and if enough mass is packed inside a small enough region, inside its Schwarzschild radius, space closes over it and forms a black hole, sealed behind an event horizon. This is general relativity, tested by bending starlight, and by the black holes we have now photographed. Now put the chain together and pull it tight. To measure a smaller distance you need higher energy, which means more mass, concentrated in that smaller region. But the smaller the region, and the larger the mass, the closer you come to packing that mass inside its own Schwarzschild radius. There is a distance at which these meet, where the energy required to resolve the distance is exactly the energy that, concentrated there, forms a black hole the size of the very region you are probing. That distance is the Planck length. Try to go below it, and the conclusion is forced. To resolve a distance smaller than the Planck length, you must concentrate so much energy in so small a region that it collapses into a black hole before you can take the measurement. The thing you wanted to see vanishes behind a horizon. The probe does not reveal the small region. It buries it, and no light, no signal, no information can come back out from behind that horizon to tell you what was there. The measurement does not merely fail, it destroys its own target and seals the result away. That is the paradox in one breath. Looking closer requires more energy. More energy means more mass in the spot, and past a certain point that mass makes a black hole that hides the spot. Below the Planck length, every possible act of measurement defeats itself. The wall is not made of our limitations. It is made of the deepest laws we know, quantum mechanics and gravity, agreeing for once and agreeing to shut the door. This is a genuine result, solid and respected. But we must now be careful and honest about exactly what it does and does not prove, because it is easy to overreach, and the honest version is more interesting than the overreach. Here is where we must be most careful, because this is the place where the story is most often told wrong. It is tempting to say that the Planck length is the smallest length that exists, the size of the tiniest possible piece of space, a kind of pixel out of which reality is built, like the little squares that make up an image on a screen. That is a vivid picture, and you will hear it stated confidently in many places. But it goes beyond what we have actually shown, and the honest scientist has to say so plainly. What we have shown, carefully and rigorously, is something more modest and in a way more interesting. We have shown that the Planck length is the smallest length that can be measured. It is a limit on knowledge, on probing, on what any conceivable instrument can resolve. Below it, measurement defeats itself by making a black hole. That is a statement about the act of looking, about the relationship between observer and observed. It is not by itself a statement about whether space continues to exist in finer detail beneath that limit, unmeasured. These two claims feel similar but are deeply different. One says we cannot see below this length. The other says there is nothing below this length to see. The first follows from the physics we have built. The second does not follow from it, at least not yet. It is entirely possible, as far as our argument goes, that space is perfectly smooth and continuous all the way down, infinitely divisible, but that this fine structure is simply hidden from us forever behind the black hole wall. A smooth space we can never probe below the Planck length would look exactly the same to us as a grainy space whose grains are the Planck length. Our argument cannot tell them apart. There is an old worry in philosophy and science about whether things we cannot even in principle observe should be said to exist or not. The Planck length sits right on that knife's edge. The honest position, the one most physicists hold, is to say clearly what we know and clearly what we do not. We know measurement stops at the Planck length. We do not know for certain whether space itself has a smallest grain there, or continues smoothly beneath, or does something stranger that neither word captures. Anyone who tells you the answer with full confidence is reaching past the evidence. That said, the suspicion runs deep that something real does happen to space at this scale, not just to our ability to measure it. The reason is the one we touched earlier. When you try to describe physics at the Planck length, the two great theories we use, quantum mechanics and general relativity, do not merely become hard to apply. They begin to give answers that contradict each other and produce nonsense. That breakdown is not about measurement. It is about the theories themselves failing, and a theory failing at a particular scale is often a hint that something genuinely new and physical is going on there. So the careful summary is this. The Planck length is, for certain, the floor of measurement, the smallest length any tool could ever resolve, and that much our black hole argument proves. Whether it is also the floor of space itself, the smallest real length, the true grain of reality, is an open and serious question, not a settled fact. We should hold the proven part firmly, and the speculative part lightly, and never let the second borrow the certainty of the first. To see why so many physicists suspect the deeper story, that something physical really does happen at this scale, we need to look closely at how exactly our two best theories break when we push them together down to the Planck length. To feel why the Planck scale troubles physicists so deeply, you have to understand that our two greatest theories of the physical world do not get along. Each is magnificent in its own domain. Each has passed every test thrown at it for a century, and each, in its own way, calls the other wrong. Most of the time this quarrel does not matter, because the two theories rule different kingdoms and rarely meet. At the Planck length, they are forced into the same room, and the quarrel turns into open contradiction. The first theory is general relativity, Einstein's account of gravity as the smooth bending of space and time. Its picture of space is elegant and continuous, like a perfectly smooth rubber sheet that curves gently under mass. In this picture, space has a definite shape at every point, and that shape changes gradually from place to place. There is nothing jittery or uncertain about it. You can zoom in as far as you like and the curvature stays smooth and well defined. General relativity rules the world of the very large, the planets, the stars, the galaxies, the whole sweep of the cosmos, and there it is flawless. The second theory is quantum mechanics, the account of the very small, the world of particles and atoms. Its picture of reality is the opposite of smooth. Down at small scales, everything jitters and fluctuates. Position and momentum cannot both be pinned down. Energy can flicker into and out of existence for brief moments, and nothing has a perfectly definite value. The quantum world is restless, grainy, probabilistic, always trembling. Quantum mechanics rules the world of the very small, and there it is flawless too. Now bring them together at the Planck length. At that scale, you have something both very small and, because of all the concentrated energy, very heavy, so both theories must apply at once. Quantum mechanics insists that space and energy at this scale must be jittering violently, fluctuating wildly from moment to moment and point to point. But general relativity says that energy bends space, so if energy is fluctuating wildly, then the very shape of space must be fluctuating wildly along with it. The smooth rubber sheet of relativity is being shaken to pieces by the quantum trembling. Space can no longer be smooth and well-defined, because the quantum rules forbid anything that's small from holding still. When physicists try to write this down, to combine the equations of quantum mechanics with the equations of general relativity at the Planck scale, the mathematics falls apart. The calculations start producing infinities, answers of infinite size where there should be sensible finite numbers. An infinity in a physics calculation is not a real prediction. It is the theory's way of screaming that it has been pushed past its limits, that it no longer knows what it is talking about. The smooth space of relativity and the jittery rules of the quantum simply cannot both be true at the Planck length. One or both must give way. This is what people mean when they say physics breaks down at the Planck scale. It is not poetry and not exaggeration. It is the concrete fact that our two best, most thoroughly tested theories, asked to describe the same tiny region, return contradiction and nonsense. Somewhere on the way down to the Planck length, the picture of space we have been using stops being even approximately right, and we do not yet know what replaces it. So the breakdown at the Planck length is real, and it is a breakdown of the theories themselves, not just of our instruments. That is the strongest hint that something physical, not merely something about measurement, is waiting at this scale. To describe it, we would need a single theory that contains both gravity and the quantum at once, and finding that theory is one of the great unfinished tasks of physics. The missing theory has a name, even though no one has finished writing it. It is called quantum gravity, and it would be a single framework in which Einstein's gravity and the quantum world are no longer separate quarrelling theories but two faces of one deeper description. Finding it is widely seen as the most important unsolved problem in fundamental physics, the prize that has occupied many of the finest minds for the better part of a century, so far without a complete and tested answer. The need for it is exactly the contradiction we just saw. We have one theory, general relativity, for gravity and the large smooth universe, and another, quantum mechanics, for the small jittery world of particles. They work beautifully apart. They contradict each other when forced together at the Planck scale. A complete theory of quantum gravity would dissolve that contradiction, telling us what space and time actually do when they are both very small and very strongly curved, in the one regime where neither current theory can be trusted alone. Why is this so hard? Part of the answer is that the place where we most need the theory, the Planck scale, is the place we can least reach with experiment. In every other part of physics, when theorists were confused, experiments came to the rescue, showing which guesses were right and which were wrong. New data pruned the bad ideas, but the Planck length and the Planck energy are so far beyond what any instrument can reach that theorists working on quantum gravity have, for the most part, been forced to work almost blind, guided by mathematical consistency and beauty rather than by the steady correction of experiment. It is like trying to draw a detailed map of a country no one is allowed to visit. There is a second deep difficulty. Quantum mechanics, in its usual form, treats space and time as a fixed, smooth stage on which particles act out their quantum dramas. The stage itself does not jitter. But general relativity says that space and time are not a fixed stage at all. They bend, stretch, and respond to what is in them. So to quantize gravity is to apply quantum rules to the stage itself, to let space and time fluctuate and become uncertain. That is far harder than anything quantum mechanics had to do before, because there is no longer a steady background to stand on. The very arena is part of what trembles. Many of the failures and false starts of quantum gravity trace back to this single strange demand, that the stage must be made quantum along with the actors. Despite the difficulty, the effort has not been idle. Over the decades, a handful of serious candidate theories have grown up, each a different guess at what quantum gravity might look like, each with its own picture of what happens to space at the Planck length. None has yet been confirmed, because none can yet be tested at the scale where it matters. But they are not idle dreams either. They are careful, mathematically demanding attempts to describe the indescribable region, and several of them share a striking feature. Almost all of them, by different routes, end up suggesting that there is something special about the Planck length, that space at that scale is not the smooth, continuous thing we're used to. In other words, the leading guesses about quantum gravity tend to agree, against our earlier caution, that the Planck length probably is more than a limit of measurement, that something physical really does change there. They disagree sharply about what. Over the next chapters, we'll walk through the main pictures, one at a time, and see how each imagines the bottom of the world. The first and oldest of these pictures came, fittingly, from the same physicist who gave the black hole its name. The first and most evocative picture of what space might do at the Planck length came from John Wheeler, the American physicist who popularized the term black hole. Wheeler had a gift for vivid images, and in the 1950s he coined another that has stuck ever since. He suggested that at the very smallest scales, space is not the calm, smooth emptiness we imagine, but a seething, restless, ever-changing froth. He called it space-time foam, and sometimes quantum foam. To understand the idea, picture how the ocean looks from different heights. Seen from an airplane window far above, the sea is a smooth blue sheet, flat and calm with no detail at all. Come down lower, in a boat, and you see gentle rolling waves on its surface. Get right down close, with your face near the water in a churning sea, and you find chaos, spray and bubbles and foam, the surface breaking apart into a frothing, ever-shifting mess that has no smooth shape at all. Wheeler proposed that space is like this. Viewed at human scales, or even at the scale of atoms, it looks perfectly smooth, like the ocean from the plane. But zoom down toward the Planck length, and that smoothness dissolves into a violent foam. The engine of the foam is the quantum jitter we met earlier. Quantum mechanics says that even in completely empty space, energy is never perfectly still. It fluctuates, flickering up and down moment to moment, and these fluctuations grow more violent the smaller the region you look at. At everyday scales, the jitter averages out to nothing and space looks calm, but at the Planck length the fluctuations become enormous, and because energy bends space, those wild energy fluctuations mean wild fluctuations in the shape of space itself. Space at the Planck scale, in Wheeler's vision, would be constantly bending, twisting and reconnecting, with tiny black holes and strange shapes flickering into being and vanishing again in less than a Planck time. It would have no fixed, smooth geometry at all. It would churn. In this picture, the very ideas of distance and direction begin to lose their meaning below the Planck length. Asking what is to the left of a point, or how far apart 2 points are, assumes a stable, smooth space in which left and distance make sense. But if space at that scale is a boiling foam, reforming faster than the shortest meaningful tick of time, then those questions may simply have no clean answers. The foam is not a thing sitting inside space. It is what space itself becomes when you look closely enough, and it is the reason the smooth, continuous picture of relativity cannot survive down there. Wheeler's space-time foam is not a complete theory. It is more of a guiding image, a way of saying that something dramatic and turbulent happens to the structure of space at the Planck scale, without specifying the full mathematics. But it has shaped how physicists think for decades, and it captures, in one memorable picture, the lesson of the last 2 chapters. The smooth space of our everyday world and even of relativity is an average, a calm surface seen from far away. Down at the Planck length, that average breaks down into a quantum storm. The foam is a picture, not a finished theory. To turn the intuition into real mathematics, into a genuine candidate for quantum gravity, with a definite shortest length built in, physicists have developed more complete frameworks. The most famous of them replaces the very idea of a point particle with something that, all by itself, refuses to be smaller than a certain size. The most famous candidate for a complete theory of quantum gravity is called string theory, and at its heart is one simple, radical change to the picture of matter. For a century, physicists had imagined the fundamental particles, the electron, the quarks inside a proton, as points, objects with no size at all, located at a single spot in space. String theory says that picture is wrong at the deepest level. The fundamental objects are not points, but tiny one-dimensional strings, little loops or lengths of vibrating something, far too small to see, and the size of those strings is right around the Planck length. The central idea is as elegant as it is strange. Just as a single violin string can vibrate in many different ways, producing many different musical notes, a fundamental string can vibrate in many different patterns, and each pattern of vibration appears to us as a different particle. One mode of vibration looks like an electron, another looks like a quark, another, importantly, looks like the particle that carries gravity. In this view, the bewildering zoo of particles in nature is not a collection of unrelated points, but a single kind of object, the string, singing in different keys. The whole material world becomes in a sense music played on these unimaginably small strings. What matters most for our story is what this does to the idea of distance. If the most basic objects in nature are not points but strings of about the Planck length, then it stops making sense to talk about anything smaller. You cannot probe a distance shorter than your shortest probe, and in string theory there is nothing shorter than a string. The string is the smallest meaningful object, so the Planck length, roughly, becomes the smallest meaningful distance, not by an outside argument about black holes, but built right into the fabric of the theory. String theory has a shortest length woven into it from the start. There is a beautiful technical feature here that deepens the point. In string theory, because the probe is itself an extended string rather than a point, trying to concentrate more and more energy to look closer eventually stops helping. Past a certain point, pumping in more energy makes the string longer, not the resolution finer, so you start probing larger distances again, not smaller ones. The very tool refuses to resolve below the string scale. The shortest length is not a wall you crash into. It is a floor the theory will not let you step below, no matter how hard you push. String theory is mathematically rich and has drawn many of the most talented physicists of the last few decades. It naturally includes a particle that behaves exactly like the carrier of gravity, which is a major point in its favour, since any theory of quantum gravity must contain gravity. But it comes at a price that troubles many. The mathematics seems to require extra dimensions of space beyond the three we know, curled up too small to see, and it allows for an enormous number of possible versions, with no clear way yet to pick out the one that describes our universe. And, like all quantum gravity ideas, it has not been tested at the Planck scale because we cannot reach it. String theory is one serious answer to what lies at the bottom, a world of vibrating strings with the smallest length built in. But it is not the only serious answer. A very different theory starts from the opposite end, not by changing what matter is, but by changing what space itself is made of, and it too produces a smallest length in an even more direct way. The other leading candidate for quantum gravity takes a completely different path, and many find it the more direct of the two. It is called loop quantum gravity, and where string theory changes what matter is made of, loop quantum gravity changes what space itself is made of. It asks the boldest version of our earlier question. What if space is not smooth and infinitely divisible at all, but is instead built from tiny, indivisible chunks, like a fabric woven from individual threads, with nothing in between the threads? In ordinary physics, including general relativity, space is treated as a smooth continuum. You can take any region and divide it in half, then in half again and again forever, with no smallest piece. Loop quantum gravity proposes that this is an illusion that holds only at large scales, and that if you could look down toward the Planck length, you would find that space comes in discrete pieces. Area and volume, in this theory, cannot take just any value. They come in specific smallest amounts, multiples of a tiny fundamental unit, the way money comes in whole cents and cannot be divided into half a cent. There is a smallest possible area and a smallest possible volume, and both are set by the Planck scale. This is a striking claim, so let us be clear about how strong it is. In loop quantum gravity, the smoothness of space is not fundamental. It is what you get when you stand far enough back from something that is actually grainy. Just as a beach looks like a smooth tan surface from a distance, but is made of separate grains of sand up close, or a photograph in a newspaper looks like continuous shades of grey, but is really a pattern of tiny dots. Space, in this view, is the smooth-looking large-scale appearance of an underlying network of discrete chunks, and the size of those chunks is around the Planck length. Below that size there is no smaller piece of space, because space is not made of anything smaller. The question, what is halfway across the smallest chunk, has no answer, because there is no halfway. The theory describes this grainy space with a particular mathematical structure, a web of lines and nodes, sometimes called a spin network, where the nodes carry units of volume and the connections carry units of area. You do not need the details to grasp the core idea. Space is not a smooth stage, but a vast network of tiny quantum pieces, and what we experience as smooth distance is really a count of how many pieces lie between here and there. Time, in some versions, becomes grainy too, ticking in smaller steps rather than flowing continuously. If loop quantum gravity is right, then the smallest length is not merely the limit of measurement that our black hole argument gave us. It is the actual grain of reality, the size of the smallest piece of space there is, and the answer to our earlier honest question would be that yes, space really does have a bottom, and it sits at the Planck scale. The limit of measurement and the limit of space would turn out to be the same thing for a deep reason. You cannot measure below the smallest chunk because there is nothing below it. Loop quantum gravity and string theory disagree about almost everything, including whether space is fundamentally grainy or whether strings live in a smooth space. They have not been reconciled, and neither has been confirmed. But there is a third strand of evidence, born from black holes themselves, that hints at something stranger than either, a clue written on surfaces. There is a third clue about the bottom of the world, and it came not from imagining tiny strings or grains, but from thinking hard about black holes themselves. It begins with a young physicist named Jacob Bekenstein in the early 1970s, then a graduate student who asked a question that sounds almost too simple. Black holes swallow things. The things they swallow carry disorder, what physicists call entropy, a measure of how many ways a thing's pieces can be arranged. So what happens to that disorder when it falls in? If it simply vanishes, then a deep law of physics, that total disorder never decreases, would be broken every time a black hole ate something. Bekenstein argued that the disorder cannot vanish, and so a black hole must itself possess entropy, must itself be a thing of enormous hidden disorder. And then he found something astonishing about how much. The entropy of a black hole, the measure of all the hidden information it contains, is not proportional to its volume, as you would expect for an ordinary object. A box of gas holds disorder throughout its volume, so more volume means more disorder. But a black hole's entropy is proportional to the area of its event horizon, the two-dimensional surface around it, not the three-dimensional space inside. The information content of a black hole is written on its surface, not packed through its interior. At first, this was just a daring proposal, but then Stephen Hawking, working on the quantum behavior of black holes, made it concrete and exact. Hawking showed, to his own initial surprise, that black holes are not perfectly black after all. Because of quantum effects right at the event horizon, they slowly glow, emitting a faint radiation now called Hawking radiation, which means they have a real temperature and, by the laws connecting heat and disorder, a real entropy. And when Hawking calculated that entropy precisely, it matched Bekenstein's idea exactly. The entropy was proportional to the horizon's area, and the natural unit in which to count it, the size of one unit of that information, turned out to be the Planck length squared, a tiny square of space about a Planck length on each side. Sit with that. The total amount of information a black hole can hold is in effect the number of tiny Planck-sized squares that tile its surface. Each little square of horizon, one Planck length on a side, holds about one bit of information, one basic yes or no. The Planck length appears here not as a limit on a ruler, but as the size of the fundamental tile of information in the universe. It is as if the surface of a black hole is a screen, and its pixels are Planck-sized. This led to one of the strangest and most influential ideas in modern physics, the holographic principle, developed by Gerard 't Hooft and Leonard Susskind. If all the information about everything inside a black hole is written on its two-dimensional surface, perhaps that is true of any region of space. Perhaps the full three-dimensional contents of any volume can be completely described by information on its two-dimensional boundary, the way a flat hologram can store a full three-dimensional image. The universe might be, in this deep sense, like a hologram, its true description living on a surface, written in Planck-sized pixels. The holographic clue does not pick between strings and loops, but it points firmly in the same direction as both. The Planck length keeps appearing as the natural size of the smallest meaningful piece, whether of space, of information, or of measurement. Three different roads, the black hole limit, the candidate theories, and now the counting of information, all arrive at the same tiny length. All of this remains theory, untested at the scale where it matters. So the fair question is whether we can ever do better than argue. Can we ever actually catch a glimpse of the Planck scale with a real experiment? After all this theory, a hard and fair question presses in. If the Planck length is so absurdly far below anything we can reach, if no accelerator we could ever build comes within a factor of 1,000 trillion of the needed energy, then is this all just untestable speculation? Is there any way, even in principle, to catch a real glimpse of the Planck scale, or are we condemned to argue forever about a region we can never touch? The honest answer is that direct measurement is hopeless, but clever indirect attempts are real, and a few are underway. The trick behind every one of them is the same. If you cannot reach a tiny scale head-on, look for a tiny effect from that scale that gets added up over a huge distance, or a long time until it grows large enough to notice. A single Planck-sized wrinkle is invisible, but trillions of them, accumulated across the universe, might leave a mark we can catch. This is the strategy of patience, letting the cosmos do the amplifying that our machines cannot. One example involves light from gamma-ray bursts, the most violent explosions in the universe, often billions of light-years away. If space at the Planck scale is grainy or foamy rather than perfectly smooth, then light of different energies might travel through it at very slightly different speeds, the higher energy light tripping over the graininess a little differently than the lower energy light. Over a few meters, this difference would be far too small to ever detect, but over billions of years of travel across the cosmos, even an unimaginably tiny difference per meter could add up to a measurable gap in arrival times, with some photons from the same burst arriving a moment before others, purely because of their energy. Telescopes in space have watched for exactly this, comparing when high and low energy light from distant bursts arrives. So far, these observations have mostly seen the different energies arriving together, in lockstep to remarkable precision. That is itself a real result. It rules out some of the simpler pictures of grainy space, the ones that predicted a larger effect, and tells us that if space is grainy, its graininess is even subtler than those models supposed. A null result, a careful nothing, still narrows the field of possibilities, and that is real progress, even if it is not the discovery anyone hoped for. Another approach uses the exquisite sensitivity of gravitational wave detectors, the giant instruments called LIGO that in 2015 first caught the ripples in space from two distant black holes colliding. These machines measure changes in length far smaller than a proton, by bouncing laser light along kilometers-long arms and watching for the faintest shift. Some physicists wondered whether such delicate instruments might detect a faint constant jitter in space itself, a kind of holographic noise predicted by certain Planck-scale ideas, the trembling of the space-time foam leaking up into our world. A dedicated experiment built to hunt for exactly this jitter looked and did not find it, again ruling out a specific prediction and tightening the constraints. This is what real frontier science often looks like. Not a triumphant direct measurement, but a patient ruling out, an ingenious search that mostly returns careful nothings, each one quietly shrinking the space of what could be true. We have not glimpsed the Planck scale directly, and we may never, but we are no longer entirely blind to it. The cosmos itself, through its most distant explosions and most violent collisions, has begun to send us faint, indirect news from a scale our machines can never reach. Even without reaching the Planck length, physicists have found a way to write its lesson directly into the rules, by repairing the very uncertainty principle that started this whole climb. There is one more development worth understanding, because it brings the whole story full circle, back to Heisenberg's trade where the real argument began. Recall that the uncertainty principle, in its original form, says that the more precisely you fix a particle's position, the larger the uncertainty in its momentum. In that original form there is no flaw. You can always, on paper, demand a smaller and smaller position uncertainty, paying with ever larger momentum, with nothing to stop you going down forever. The principle itself contains no smallest length. The wall came only later, from gravity. But what if you took the lesson of this entire journey, that gravity stops you below the Planck length, and folded it directly back into the uncertainty principle itself? That is what physicists have done with an idea called the generalized uncertainty principle. It is a modified version of Heisenberg's rule, adjusted to include the effect we have spent the whole script uncovering: the fact that at very high energies, the probe begins to make a black hole, and the resolution starts to get worse instead of better. In the ordinary uncertainty principle, increasing the probe's energy always tightens the possible position with no limit. In the generalized version, an extra term is added that captures the gravitational backfire. At low energies, this term is utterly negligible, and the rule behaves exactly like Heisenberg's familiar one, so all the ordinary successes of quantum mechanics are preserved. But as the energy climbs toward the Planck scale, the new term grows and begins to fight back. Push the energy higher to shrink the position uncertainty, and at first it works, but past the Planck scale the extra gravitational term takes over, and the position uncertainty starts growing again. The harder you push, the worse it gets. The result is that the position uncertainty can never drop below a certain smallest value, and that smallest value is, of course, right around the Planck length. The generalized uncertainty principle has a minimum length built into its very mathematics. It cannot describe a position pinned tighter than the Planck length, because the rule itself forbids it. The flaw we discovered through the long chain of wave limits, energy, mass, and black holes is now sitting inside a single modified equation as a basic feature of the relationship between position and momentum. This is a satisfying place for the argument to arrive. We began with Heisenberg's clean trade, which had no flaw and seemed to allow endless sharpening of position. We followed the consequences out through relativity and gravity, and found that, in the real universe, there is a flaw after all. And now that flaw has been written back into the trade itself, turning Heisenberg's principle into a new rule that knows about its own limit from the start, the journey out and the journey back have closed into a loop. The smallest length is no longer an external wall the principle runs into. It has become part of the principle. The generalized uncertainty principle is not a complete theory of quantum gravity either, and its exact form is still debated, with different versions adding the gravitational term in slightly different ways. But it shows something important. The idea of a smallest length is not foreign or awkward to physics. It can be built smoothly into our existing rules, modifying them gently in just the right way, leaving everything we already know untouched while quietly closing the door at the bottom. The Planck length fits naturally into the structure of physics, as if it always belonged there. We have traced the whole argument, met the theories, and seen the attempts to test them. It is time to step back and ask what this strange limit, this flaw at the bottom of all measurement, finally means. Step back now and consider what this limit really teaches, beyond the physics itself. We began with the simplest, most confident assumption a person could make, that with enough cleverness and patience we could always build a finer ruler and measure something smaller, forever, with no bottom anywhere. It seemed obvious. Nothing in the plain act of measuring suggested a flaw, and yet, following honest physics step by careful step, we arrived at a wall woven into the universe, a smallest length below which the very act of looking defeats itself. That arrival carries a lesson in humility, but a particular and interesting kind of humility. It is not the ordinary humility of saying our tools are weak and someday a cleverer person will do better. That is the humility of engineering, and it has been overturned again and again throughout this very story, by sharper lenses, shorter waves, and faster particles. This is a deeper humility. The wall at the Planck length is not a statement about the poverty of our instruments. It is a statement about the structure of reality, which has arranged things so that some knowledge is not merely hard to get, but impossible to get, sealed off by the same laws that make the universe work at all. There is something almost poetic in how the door is shut. It is not shut by a barrier placed in our way, like a locked vault we lack the key to. It is shut by the cooperation of the two grandest theories we have, quantum mechanics and gravity, the science of the smallest, and the science of the largest, which spend most of their time ignoring each other and then, at this one scale, join hands specifically to stop us. The very curvature of space that lets stars and planets and orbits exist is the same curvature that, concentrated, becomes the black hole that hides the Planck scale from view. The universe protects its smallest secret using its largest tool. And notice the strange role of the observer in all this. Through most of science, we imagine ourselves as outside watchers, looking in at a world that does not care whether we look. The Planck length breaks that comfortable picture. Here, the act of observing is not separate from the thing observed. To look hard enough at a tiny region is to change it utterly, to pour in so much energy that you collapse it into a black hole and seal it away. The watcher and the watched are bound together, and past a certain closeness the watching destroys the watched. Knowledge has a cost, and at the bottom the cost becomes the loss of the very thing you sought. This does not make the universe smaller or sadder. If anything, it makes it richer. A world we could measure all the way down with no flaw would in a sense be fully open to us, exhausted in principle by enough patience. A world with a genuine bottom to measurement is a world that keeps something for itself, that holds a final reserve no instrument can ever reach. The Planck length marks the edge of the knowable, and an edge to the knowable is not a defeat. It is a feature of a universe deep enough to contain its own horizon of knowledge. So the limit teaches us where understanding meets its honest end, and asks us to hold both things at once, the magnificent reach of what we have learned, and the firm wall at the bottom of it. We have measured atoms, split them, peered inside their nuclei, and found a flaw only at a scale 100 million trillion times smaller than the atom. That is not a small achievement humbled. It is an enormous achievement that has finally honestly found its edge. With that in mind, let us return one last time to the simple question we started with, and answer it plainly. We started with a ruler against a table, and a question that seemed almost childish in its simplicity. How small can a measurement go, and what could possibly stop a perfect instrument? We can now answer it plainly, in the simplest words, having earned every step of the answer. Measurement stops at the Planck length, about a millionth of a billionth of a billionth of a billionth of a meter. It stops there not because our instruments are crude, and not because we are too early in history, but because the universe itself closes the door. To measure a length, you must probe it. To probe something that small, you must concentrate enormous energy into a tiny space. That energy is mass, and mass packed tightly enough becomes a black hole. So any attempt to measure below the Planck length pours in so much energy that it collapses the very region into a black hole, sealing the answer behind a horizon from which no news returns. The closer you try to look, the more the universe pushes back, until looking itself becomes the thing that hides the truth. That is the whole answer, and it is honest. We should hold the proven part and the open part clearly apart, as we promised. It is certain that the Planck length is the smallest length we could ever measure. It is not certain, though widely suspected, that it is the smallest length that exists, the true grain of space. The honest frontier is exactly here. Our two best theories break down at this scale and contradict each other, and the unfinished theory that would join them, quantum gravity, is the great open problem. The leading guesses, vibrating strings, grains of space, information written in Planck-sized pixels on surfaces, all point towards something real happening at this length, but none has been confirmed because the scale lies so far beyond our reach. We have caught only faint indirect hints, mostly careful nothings, from distant explosions and trembling detectors. Now widen out, because this small length touches something large. You're made of atoms, and those atoms are mostly empty space, with tiny dense nuclei at their hearts. Below those nuclei lie quarks, and far, far below the quarks, 100 million trillion times smaller than the atoms that make you, lies this floor, the Planck length, the place where space and time as we know them may dissolve into something we have no words for yet. It is the bedrock beneath the bedrock, the scale at which the stage your whole existence plays out upon was first set, in the opening sliver of the universe, 1 Planck time after the beginning. And here is the quiet wonder to carry away. You, a creature of ordinary size standing between the vast cosmos above and this unreachable smallness below, have managed to reason your way down to the very bottom of measurement. You cannot go there, no one can, no tool ever will. And yet, sitting with pencil and thought, and a few measured constants of nature, human beings worked out exactly where the bottom is and exactly why it is forbidden. We found the edge of the knowable not by reaching it, but by understanding the universe well enough to know it was there. That is the strange gift of this whole story. The Planck length is a wall, but knowing the wall is there, knowing precisely how far down it sits and what laws build it, is itself a kind of seeing. We cannot measure below it, but we can understand it. And understanding, it turns out, can reach places no ruler ever will, all the way down to the smallest meaningful length in the universe you're part of.